I spent 2 hours. Like, this is the most elaborate demonstration. Oh,
that worked.
That's when you give the whistle.
Sorry, it gives me joy. But anyway, my apologies for your eardrums. Let's begin. Heavenly Father, we thank you for this day. Thank you for these students, and just pray again that you guide our steps and just help us to understand a little bit more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. So today we are doing rotational motion. My apologies, I do not have your test graded yet. I started grading it, and many of you did pretty well on problem 1, so woohoo! But not all. But oh well, these things will happen. So rotational motion, for example, like this. Let's see here if I can illustrate. Oh man, won't quite fit. Yeah, let's see if I can figure something out here. There we go. Oh, whoa, uh-oh. Well, that's not going to work. Yeah, we just went through it. Well, yeah, it just pulled through. Let me just be lazy and tie it. I used to have a yo-yo sitting around, but I don't know where it went to. But in the absence of a yo-yo, you could ask a question, you know, like motion like this. How does this work? You can see that. So like circular motion, right? How would you describe that kind of thing? Motion that is basically rotational in nature. So that's what we'd like to start talking about in this this part of the course. So that said, there are 2 paths we can go down right now. And I'm going to let you guys decide. I'm going to take a poll. Show of hands, who wants to talk about rotational motion today? All right, well, that's the other option. Fair enough? So at some point in the near future, we'll also have to talk about something called the cross product, which is something you do with 2 vectors to make a third vector. So we can either wait and cover that in the midst of the material, or I could just cover it right now. So what's your preference? Cross product in the middle or cross product now? Now? Okay, cool. So definition. A cross B is a vector defined by the following. So there's various techniques, but the one thing is just to write down the formula for it. And the formula for it is, so in the first slot, you're going to do A2 times B3 minus minus A3 times B2. And then you're going to have a comma. And then you're going to write A1 B3 minus A3 B1. Then you're going to have another comma. And then you're going to write A1 B2 minus A2 B1. And that serves as a definition. So what I just said, A2 B3 minus A3 B2 comma A1 B3, wait a minute, A3 B1 rather, minus A1 B3, comma A1 B2 minus A2 B1. So this is the definition of the cross product of 2 vectors. Now, if you've had Calculus 3, some of you, you also learned this mnemonic. There's a mnemonic for this. You can say it's the determinant. You put x hat up here, y hat here, z hat here, and you put A1 A2, A3 like so, B1, B2, B3 like so. And that's a lovely formula if you know what a determinant is. Do you guys know what a determinant is? Some of you are taking Math 221? No, I think we talked about this already. No one's taking Math 221, right? If you were, you learn a determinant in there, and this formula becomes meaningful. But anyway, this right here is just a shorthand for saying you do like x hat times A2B3 minus A3B2, all right? And so forth, all right? Y hat times, A3B1 minus A1B3 plus Z hat times A1B2 minus A2B1. All right, now I've written the same formula twice. Lovely. Wonderful. Okay, but anyway, however you want to write the formula, you can. The question is, why? What's the purpose of this new vector that we're creating, right? And the answer is relatively simple. And let me show you what it does. So let's calculate. What happens if we take the dot product of A and A cross B? What do you get then? Do you guys remember the dot product? I hope. So we do what? We do A1 times what? Times A2 B3 minus A3 B2 plus what? Plus A2, right? So remember that A has the form A1, A2, A3. So when we calculate the dot product of A with A cross B, we have to do the first component of the one times the first component of the other, and then we do the second component of the one vector times the second component of the other. This is how we take dot product. So I have A2 times A3 B1 minus A1 B3. And then finally plus A3 times A1 B2 minus A2 B1. So there are 6 terms there, right? Now let's focus our attention here. A1, A2, B3. Do you see that anywhere else? See this term? Is there A1, A2, B3 anywhere else in this? How about right here? A2, A1, B3. That's the same term with just A1 and A2 flipped around, right? But A1 and A2 are just numbers. They're components of the vector, so they commute. But you notice that you've got the same thing, but with a minus. They cancel, right? How about the next term? A1, A3, B2. Where else is that? Over here, right? A1, A3, B2. That's this term. See that? You have a minus in the first one. You got a plus on the second one. They cancel, right? What's next? We have this A2, A3, B1 term. Where else do we have one of those? How about over here? A3 times A2 times B1. However, what's the difference? Plus and minus, right? So we have 6 total terms, and they cancel in 3 pairs. And what's the net result? 0, right? 0. So what I've just shown you is that if we define the cross product as I have, then A dot A cross B is equal to 0. All right? Guess what else is 0? If we do the same calculation with B instead of A, you can also prove that B dot A cross B is equal to 0. Yes, sir? The order is significant. It's not commutative. So I'll say more in just a second. But so what do these 2 equations mean here? What do these say? What's the relation geometrically of A and B to A cross B? They're perpendicular, right? So this means that the vector A cross B is perpendicular to both A and B. Now, does that uniquely define a vector? Like if I told you, you take two vectors and you want to create a third vector which is perpendicular to both of them, right? Think about that. Does that uniquely define a vector? So here's my two vectors, right? And then I think about those vectors, they'll lie in some plane, right? If they're non-zero vectors, you give me two vectors, as long as they're not collinear, they define a plane, right? So if you're looking for the vector which is perpendicular to those, you're looking for what's called the normal to the plane, right? So is the normal to the plane uniquely defined? Well, no. There's infinitely many choices for the normal to a plane. Oh, come on. There we go. So the normal to the plane could go like this, right? Or it could go like that, right? It could go up or down. And also the normal to the plane, how tall is the normal to a plane? Well, it could be this tall, right? It could be this tall, right? That's still perpendicular to both vectors. If I add another marker, it's still perpendicular to my two original vectors, right? So there's not a unique answer to the question. Given two vectors, how do you find a third vector perpendicular to the given two, right? But the cross product gives you a particular choice of that infinity of vectors. It gives you a particular vector which is perpendicular to a given pair. And the way that the cross product is defined, in particular, it is defined such that the magnitude of the cross product is given by the area of the parallelogram which is spanned by A and B. So if I draw a picture like this, A and B like this, right? I can fix the magnitude of the cross product by demanding that it be equal to the area of this parallel piped, this parallelogram here, all right? What's the area of this parallelogram? Do you guys know? Base times height, right? Do you guys remember base times height for parallelogram? So in terms of, if I put this as angle theta, right? So this height would be what? See, it would be A times the sine of theta, right? So the area of the parallelogram, anyway, with sides A and B, that's equal to the magnitude of A times the magnitude of B times the sine of the angle between them. Because that's that's the base times the height of the parallelogram, right? And it turns out that you can prove that this is equal to the magnitude of the cross product of A and B. So that's why the formula that's given is given. It turns out that if you want if you want two vectors you want to take two vectors, you want to create a third vector which is perpendicular to the first two, that does not uniquely define a vector. But if you add the assumption that it also fixes the magnitude as being equal to the area of the parallelogram of the two vectors which are input, well, that pins things down. It's still not quite uniquely fixed though, right? Because if you think about it a little bit more, you'll realize that you could still go one direction or another, right? So like, I've got, let's draw a picture. So if this is, this is A, this is B, right? They define some parallelogram, right? In the plane. So if the area of that parallelogram is the length of this green marker here, right? There would still be two choices of normal. See that? You could go up or you could go down. So there's still, this is not enough to uniquely fix the cross product. You also have to make a choice of what's up and what's down. And the way that's done is with what's called the right-hand rule. All right, so watch me here. This is my right hand, right? The way it works is you point your fingers in the direction of A, right? Now, I can do that, right? And then you're supposed to cross your fingers into the direction of B. Now, some of you would be double jointed and, provide a meaningless, you'll ruin my whole discussion. But supposing you're not double jointed and you can't bend your fingers back like this really, like I have to personally turn my hand over like this. See, this B is pointing out of the board. That's the perspective. I mean, I can only draw so much on the board, right? So here's A. Let's say here's B, right? If I point my right hand in the direction of A to curl them into the direction of B, it forces me to put my hand this way. And my thumb then will point in the direction of the cross product. So with A and B so pictured, again, the understanding B is coming out of the board, A is parallel to the plane of the board. The cross product of A and B points down like this. All right, to give you another example. If on the other hand, we have, let's say, A is pointing like this, all right? And let's make B go into the board. And so I need a picture. What should our picture be for into the board? For into the board, we'll do this picture, like this. So this means B points into board. The other picture I could draw for the previous example would be, I've got A like here, all right? And if I want to draw a picture for B coming out of the board, the standard picture for that is this, circle with a dot. The idea of this is basically like think about an arrow like this, and then it's got fins. I can't draw them, but you got 4 fins coming out the back. So if you look at the fins from the back, it makes a cross, right? Whereas the tip of the arrow is like a cone, so that's just like a circle and a dot if you look at it head on. Okay, so that we distinguish the tip of the arrow from the tail feathers of the arrow in this way. So this B points into the board, whereas this one points out. All right, so we need, unless you want to try to draw perspective, as I was doing over here, right? We need some kind of notation to be clear. And anyway, so long story short, right hand rule. All right, follow me. For this example here, we point our fingers in the direction of A. B crosses into the board, so I have to turn my hand like this, cross my fingers like that. So A cross B is up for this one. In contrast, that one, I point my fingers in the direction of A into the board, right? So, wait a minute, out of the board, my bad. So to go out of the board, just like it already is, cross, thumb's pointing down. So it doesn't, the right-hand rule doesn't precisely give you the direction, right? Because your thumb is not exactly perpendicular to your palm or anything like that, right? That just gives you a sense of the direction. It lets you choose one side of the paper or another, right? Like, for example, this book, this folder, right? This defines a plane. All right, so if I say that I've got, 2 vectors on this plane, like so, right? So I've got the green vector and the blue vector, right? And then I can ask if if I take the green vector and I cross it into the blue vector, where does that go? See, I'm trying. It's trying to roll off me. So I do right hand roll into the green, cross into the blue. I'm above the book, right? On the other hand, if I go the blue vector and cross into the green, I'm below the book. So the cross product will allow you to pick above and below a plane, is the idea. Any questions? Yep.
Can they only go like the above and below?
Well, the key idea is that it has to be perpendicular to both of the inputs. So it doesn't have to be above or below, right? If I look at, like, you know, two vectors that are, you know, oh, wait a minute, just a second here. I'm not using all of my instructional aids in this room. Ah, someone cleaned. No. Ah, there used to be a bunch of meter sticks up here. Son of a gun. Oh, wait a minute. Haha, they missed one. How do you get 2 meter sticks from one? Should I do it? Yes. I'm not on camera. I think you were. I saw that. Originally, I was told you're not on camera, and then I saw a move to put me on camera. I see you can't be trusted, so I'll have to make do with. So, like, to answer your question, if this is vector 1 and this is vector 2, see, if I put them like this, A cross into B comes back and pokes me in the head, right? On the other hand, if this is B and this is A and I do B cross into A, then I'm shooting Sam, I think. I can't quite, my hand, these are, it's a heuristic, all right? Like, it's not precise, but it gives you a sense of, because you just have to pick one side or another with the right hand rule. Okay, that said, there is absolutely nothing approximate about this formula, right? This is concrete. You give 2 vectors, you put it in. All right, you calculate the cross product. So let's actually do that. So example 1, if I have A equals to 1, 1, 2, and I have B is equal to 0, 3, 4, and I take the cross product of those. All right, so what do I got? 1 times 4 minus 2 times 3, comma, 2 times 0 minus 1 times 4, comma, 1 times 3 minus 1 times 0. Now you might say, what did I just do? Right? What did I just do? Let me draw the pattern, right? So what I did was 1 times 4 and 2 times 3. That gives me these two, right? So, like that. And then I did the 2 times 0 and the 1 times 4, like that. I don't know, it gets really busy to write it out with these silly lines. Listen, I'm just following the pattern over here that I wrote down. What's the pattern? Let me try to explain the pattern more to you. The pattern is this. Each component, you're only using the numbers from the component that you're not currently calculating. So when I'm looking at 1, I'm only using 2 and 3 components from the vectors being crossed. See that? I use the 1, 2, and the 3, 4 here. When I'm in the 2 component, I'm not using the 1 or the 3. I'm only using 1, 0, and 2, 4. All right? For the 3rd component, I'm using 1, 2, and 2, 1. Now, there's still a question of how do you choose plus or minus, right? But before we, so anyway, I'm using the formula. Now let's see if I'm right or wrong. How would you check if you're right or wrong? 4 minus 6 is minus 2, right? Minus 4 and 3. So did I make a mistake, or am I right here? How can I check? There's an easy way to check. I just have to take the dot product of my answer with the inputs, right? So let's do that and check on my work. So 112 dotted with minus 2 minus 4, 3 is equal to what? Minus 2 minus 4 plus 2 times 3 is 6. 0. Woohoo! And also, I'm supposed to take the dot product of 0, 3, 4 with minus 2 minus 4, 3. That gives me 0 minus 12 plus 12, also known as 0. So at this point, I would have to be incredibly unlucky to have calculated the cross product incorrectly. So there you go. That's the cross product of A and B. Now, let me share with you my trade secrets here. How do I remember this formula? All right, how do I put it into practice? So the first and most important thing is what I just showed you. Check your work. I'm telling you, check your work. Now, I'm telling you this, but from an actuarial perspective, if history is any guide, 40% of you will not check your work on the next test, and you will get the cross product wrong needlessly. Please, make me a liar. I want to be a liar. Prove me wrong. Everyone get the cross product right. This is not hard. You can do this, all right? It's something new. You need to study it, but you can do it. And also, you have a 3x5 card, right? So you can literally copy that formula down to carefully execute it, all right? But here's the other aspect to this. If you calculate, let's just do it. What happens when you calculate the cross product of 1, 0, 0 with 0, 1, 0? What do you get? Yes? 0, 0, 1, right. Now, there are various ways you could, of course, the most boring way would be to go back to my definition and just plug in A1 equals to 1, A2 equals to 0, A3 equals to 0, B1 equals to 0, B2 equals to 1, B3 equals to 0. The other way we could go is just think about it. You're asking for the right-hand rule. So the right-hand rule, right here, here you go. This is x hat, this is y hat. So up here, we've got z hat. So right-hand rule, x hat crossed into y hat, it has to give me z hat, because what's the area of the parallelogram with side length 1 and 1? Well, it's a square, its length is 1. So you must be talking about a unit vector for your cross product, and the right-hand rule says it's z hat, not minus z hat. So this is inevitable from that perspective as well. So what we have is x hat cross y hat equals to z hat. Wonderful. How about, what if we look at y hat cross z hat? What do we get there? Try it out. Think about the right-hand rule. Y hat crossed into z hat comes out at us, right? So this is x hat. And I know that it's not I know it's not 2 times x hat or something else, because I already know there's this wonderful formula that I told you guys, and I haven't proved it. But you guys don't make me prove anything in here, so, you know, there we go. That is true. The magnitude of the cross product is AB sine theta, where theta is the angle. What's the angle between y hat and z hat? 90 degrees, right? Y hat and z hat are perpendicular. So the angle is 90 degrees, sine of 90 is 1. So it has to be a unit vector. And then what's the other one? Z hat crossed x hat is equal to? See here, z hat cross into x hat, I get y hat, right? So let me put it in a different notation just to kind of draw your attention to the difference. There's a difference here. So notice that if we go back to like 1, 2, 3 notation, x1 hat cross x2 hat is equal to x3 hat, right? x2 hat cross x3 hat is equal to x1 hat. All right? If I use 1, 2, 3 notation, notice the difference. This one is different. This one, we have x3 hat crossed with x1 hat equals to x2 hat. That is the source of the seeming break in the pattern of the formula. If you go back and look at the formula, notice this. In the one component, notice that we have 2, 3. That's the positive one, right? 1, 2, that's the positive one. But here, we don't do 1, 3 first, we do 3, 1. Why is that? It's precisely because x3 hat cross x1 hat is equal to x2 hat. And so to make this formula aligned with this right-hand rule, it forces us to put that in that order. But once you understand clearly what the first term is in each one of these, what remains is just the negation of it. And again, the rule is each component only involves the components that you're not calculating. For the first, I look at the second and the third. For the second, I look at the first and the third. For the third, I look at the first and the second. All right? This is the formula. There's a more beautiful way of writing this. You can also write A cross B is equal to, well, if I calculate the ith component of this, it's equal to the sum over, let's say, j and k of epsilon I, j, k, a sub j, b sub k. So this is the so-called antisymmetric symbol. Here, epsilon 1, 2, 3 is equal to epsilon 2, 3, 1 is equal to epsilon 3, 1, 2 is equal to 1, whereas epsilon 3, 2, 1 is equal to epsilon 2, 1, 3 is equal to epsilon 1, 3, 2 is equal to minus 1. So there is a compact, beautiful way of writing the cross product. I did not see this in my Calculus 3. I personally was taught this by a Spanish physics student in graduate school who chided me for writing pages of needless work because I was only taught the American, stupid, this formula, which will spin your wheels for questions that are theoretical in nature about the cross product. Whereas if you know about this more concise notation, it allows you to prove things much more elegantly. There's a similar formula for the determinant, which if you take linear algebra from me, I'll show you. But anyway, so circling back, the next question that's obvious to ask here, what are the properties of the cross product, right? So what are the properties? Can you guys tell me? Props. So first of all, we've already covered the most important one, which is that A cross B is perpendicular to A and B, right? Which which is really these two identities right here, right? That's what I mean by that. The dot product with A and the dot product with B is 0. So it was asked, does the order matter? The order does matter. In particular, what is A cross B as it relates to B cross A? Minus B cross A. Very good. That's exactly right. So the next thing we usually tell students at this point is, what's the cross product of any vector with itself? 0, right. And how do you see that?
Because the sign of 0, 0.
Ah, very good. Yes, the sign is 0, 0. That's one way. Surely. Very good. The other way to do it would be like this. A cross A is equal to, minus A cross A is equal to A cross A, right? So that means that 2 times A cross A is equal to 0. So therefore, A cross A is equal to 0. I like your sign of, the angle between any vector and itself is 0, right? So very nice, very nice. But anyway, A cross A is equal to 0. Now you might say, and that is the 0 vector, right? I don't always write vector on it, but this is an important distinction to make. The cross product is a vector. In contrast, the dot product is a what? A scalar, right? What was do you remember the formula for the dot product? I should probably write it down here somewhere. If you don't mind, I'll put it, I'm gonna erase these right-hand rules. So the dot product, in contrast, was what? A dot B in 3 dimensions. That's A1 B1 plus A2 B2 plus A3 B3. This was the formula for the dot product. The dot product is sometimes called the scalar product because it gives you a scalar, a number, right? And what's the deal with the dot product? What's it equal to? Well, it's equal to AB cosine theta, right? So like, if we're thinking about contrasting the dot product and the cross product, they're very similar in some regards, right? What are the properties for the dot product? Did we ever talk about it? I don't know if we ever really talked about it in here. Yeah. Oh, yeah, I got that there. But also, how about this? A dot B is equal to B dot A, right? And we also have other properties, right? Like if you have CA1 plus A2 vectors dot B, what happens? You get CA1 dot B plus A2 dot B, right? The dot product's got this kind of linearity. That's also true for the cross product. If I have the cross product of, like, say, A with C, let's say CB1 plus B2, that is equal to C times the cross product of A with B1 plus A cross B2. So both the dot product and the cross product they have this linearity. They break up across addition. You can pull scalar multiples out of them, all right? How about the dot product of 3 things? What can you tell me about A dot B dot C? What can you guys tell me about that? I've offended Simon. Very good. Simon should be offended. This is nonsense. That's why he left. Simon's like, this is not even defined. I'm leaving the room. So I support it. Good timing. So, yeah. So why doesn't that make sense? Can you take the dot product with a number? See, because if we do it like this, A dot B is a number. Does it make sense to take the dot product of a number with a vector? It does not, right? So we didn't even ever ask this question because it didn't even make sense. How about the cross product? Can you take the cross product with the cross product? A cross B cross C. Does this make sense? Does this make sense? The answer is no. But not for the reason that you want to but not for the reason that you think. We can make sense of it, but we have to add parentheses. Now that's a reasonable expression. The reason that it's not a reasonable expression without the parentheses is that the cross product is actually a non-associative product. What is true is that if you do A cross B cross C plus B cross C cross A plus C cross A cross B, parentheses, if you do the sum of these 3 things, this is equal to 0. This is called the Jacobi identity. The principal application of this is if you're reading an engineering book and that book has the cross product of 3 vectors without parentheses, that's your heads up that your author is sloppy and doesn't quite understand what they're writing. So hopefully that doesn't happen in your engineering books, but if it does, you should demand a refund from the bookstore or something. I don't know, but yeah, if people ask me for what's a non-associative product, one of my first examples is the cross product, and the second, much more low-level example is subtraction. Subtraction's not associative, right? You start thinking about it. Okay, so enough about that. There's a mnemonic which is helpful for remembering the cross products. So like here, I just wrote them out for you, but you can write them in a circle like this. Well, usually people, I'll go back to IJK for a second here. IJK hat like this. So you just do a circle. And if you go with the circle, you keep positive. For example, like I hat cross J hat is K hat. J cross K is I hat. But if you go against the circle, for example, I cross K, you get minus J. All right. Another thing I should mention to you guys. So these are the main properties of the cross product alongside this AB sine theta formula. There is one interesting formula that mixes the two. If you do A dot B cross C, you can do that. This makes sense because we can calculate the cross product of two vectors. That gives us a vector. And then we can take the dot product with that. What do you think this is going to be? A dot, this is called the triple product. What is this calculating? What this is giving you is called the volume. So this is plus or minus the volume of the parallelepiped with sides ABC. So if I have three vectors, right? You can think about this, I just have these, like two vectors here, and then I've got a third one like this. Then that defines some little, parallelepiped. I'll draw a picture. So it's kind of like a slanted box, So this would be maybe A, maybe this one is B, and this one's C. The volume of that is given by plus or minus. Listen, if C is in the direction, let me do it the other way, my bad. This is equal to A cross B dot C, by the way. Oh, I might be wrong about that. It's plus or minus that. Just a second. This is equal to B dot C cross A, which is literally equal to C dot A cross B. And that is commutative. Okay, it is actually equal. Sorry, I had to look at something. So those are actually equal. So when is A cross B dot C going to be positive? Think about it. So if you take A cross B, right? My thumb is upward. So for the pictured one, A cross B dot C would be positive. The reason for that is that C is on the the positive side of the plane defined by A cross B. If I have A and B in that order and I take their cross product, that defines an upper direction. If C is in that direction, then this triple product is positive. So, but if my picture was wrong, if C was actually pointing down, then this would work out the negative. But anyway, this is called the triple product. If you want to calculate the volume of a parallelepiped, you can take the dot product of the cross product of the other two sides. So that's kind of handy. If you know about determinants, this is also equal to the determinant of if you just take all three vectors and you concatenate them. If you know what if you don't know what a determinant is, disregard this comment, okay? But if you do, you can just glue the vectors together and get that. Let me do another calculation here for you guys. Suppose A is equal to 1, 0, 3, and B is equal to 0, minus 2, 0. let's calculate the cross product of A and B again. Okay? How do we do that? Now, we've got options, right? We can use the formula. We can use the formula like I did earlier, but I think the better way to do this one is with algebra. So this is x hat plus 3z hat, all right? And this one is minus 2y hat. So if I want to calculate the cross product of A and B, I can use properties of the cross product to do it. So the cross product is like an ordinary product, but you have to be careful to obey the order of things. So I have minus 2 x hat cross y hat minus 6 z hat cross y hat. Now what's x hat cross y hat? What's z hat cross y hat? So I showed you the circle. There's another way. There's the line like this. X hat, y hat, z hat, x hat, y hat, and so forth, all right? And so if you do like this, this also is a way to calculate the cross product. See, x cross y is z, y cross z is x. See that? X cross y is z hat, y cross z hat is x hat. If you go this way, it's positive. If you go that way, it's negative. That's another mnemonic you can use to remember the cross products of the unit vectors. So here, x cross y hat is z hat, and z cross y hat, I got to go the other way, right? So it's minus x hat. So I get minus 6 times minus x hat, which, going back to the other notation, well, one more step. This is 6x hat minus 2z hat. So if I go back to the angle bracket notation, this is 6, 0, minus 2. There you go. What should we do whenever we calculate a cross product? We should check our answer. So what is the dot product of that with A and B? I got myself a 6, minus 6, 0 for the dot product with A, right? The dot product with B, it's just 0. So hooray, we've calculated it correctly. Here's a follow-up question. What's the area of the triangle with sides A and B? Think about this. I've got A here. I've got B here. You can think about a triangle that has those as sides, right? What's the area of that triangle? Can you guys tell me? Ah, very good. Yes, the area should be 1/2 the magnitude of A cross B. Why is that? Because if we finish the triangle to the parallelogram, it has double the area that we're interested in, right? Like the rest of it that I haven't drawn up here, same area, right? So if I just want the area of the green part, I divide by 2. So what would the area of that triangle be then? One half the square root of what? 30, yeah, 40. Thank you. 36 plus 4. So yeah, square root of 40 over 2. I guess that's square root of 10, right? Whatever units we're using today. So no units to be seen, huh? So the reason that this matters, the reason that we can't help but not talk about this at this point, is rotations are an inherently three-dimensional thing. It might not seem like that to you right at first glance, but the thing is, if I'm talking about rotations, I have to really be talking about the axis to the rotation, and the axis for a rotation it's a three-dimensional thing, because rotations happen in a plane, and the axis has to be off that plane. It has to be perpendicular to the plane, so it forces us to be three-dimensional. Although, like next class, I'll show you many formulas which don't seem three-dimensional. There's a large part of this material which doesn't require vectors. So we'll come back to this as we get into it. But anyway, thanks guys. Again, sorry I don't have your test yet. I'm working on it.